Welcome to this video about biochars from waste. I'm Capucine Dupont from IHE Delft Institute for Water Education. And today, I hope that at the end of my talk, you will be able to describe the main steps involved in the biochar production processes from waste, reflect on the technical, economic and environmental advantages and disadvantages of the main production processes and technologies associated, and lastly, evaluate the suitability between different waste types and biochar production processes. How to evaluate the suitability of one material with a conversion process. The main property of waste that defines its suitability with conversion processes is the moisture content. Moisture is the water contained in the waste. The waste can be classified into two families. On the one hand, the dry waste, which is not fully dry, but has a moisture content below 60% on wet basis. Dry waste includes, for instance, wood and co-products like branches, agricultural co-products like rice, straw, husk, and energy crops like grasses. On the other hand, wet waste contains more than 60% of water. Wet waste can be agricultural products like cereals, industrial co-products such as sludge, organic waste such as food waste, or fecal sludge. As you can see on the picture, one key point is the heterogeneity of this waste. Talking about waste as a material does not really make sense, since waste encompasses a very broad range of materials having very different physico-chemical properties, and it is crucial to keep in mind this heterogeneity when considering the conversion processes. But how to convert waste? In other words, how to turn waste into a resource. Maybe one of the most important slides now. As you can see, there are many processes giving rise to various products, including materials, chemicals, fuels, as well as heat and electricity. We are not going to enter the details of this process in the frame of this video. However, the key message to remember is that the processes are of two types. The biological processes, mainly anaerobic digestion, composting and fermentation, that are suitable for wet waste. And on the other hand, you will find the thermal processes, mainly combustion, gasification, pyrolysis, and hydrothermal conversion. For which kind of waste are these processes suitable? Well, logically, thermal processes are more suitable for dry waste, and you may know why. Indeed, the basic principle of thermal processes is to heat the material, and therefore heat the water contained in it as well. Heating water is a very energy-intensive operation, and thus a very expensive operation that will decrease the viability of the overall process. It is therefore more viable to use dry waste in such processes. This is in fact not true for all of these thermal processes. For hydrothermal conversion, and you can guess it from the name, hydrothermal, water is not an issue. On the contrary, water is required in this process. But we will come back to this later. What you can remember is that for most thermal processes, you are more suitable when you have dry waste, except hydrothermal processes that are suitable for both, and mainly wet waste. Especially in the field of sanitation, one major advantage of thermal processes is that they operate at high temperature, typically more than 300 degrees Celsius. And under these conditions, the question of pathogens in waste is solved without any discussion possible. No pathogen survives at 300 degrees Celsius, and thus no pathogen survives any thermal process. But let's now focus on the core of this video and on the production processes of biochar. Two thermal processes can be used, pyrolysis and hydrothermal conversion. And let's start with pyrolysis. Pyrolysis is suitable for dry waste, such as rice husk. These materials need to undergo first some pretreatment to fulfill the specifications required by the pyrolysis step. This pretreatment can be basically of two types: thermal, more specifically drying, to reach around 20% of water in the material, and mechanical, that is milling of the large pieces of the material to centimetric or millimetric particles. This later pretreatment makes the material easier to handle, but also it makes it more homogeneous, which is crucial to get a more constant process over time. When the material is pretreated, it is ready to enter the main step, that is pyrolysis. What is pyrolysis? It is characterized by the word that is hidden on the slide. Pyrolysis is the heating of a material in the absence of oxygen, which means absence of air in the reactor. This reaction typically occurs between 300 and 700 degrees Celsius, atmospheric pressure, and, as I told you just before, under inert atmosphere. Under these conditions, the material decomposes and releases some gas, such as carbon monoxide, carbon dioxide, and methane, as well as liquid, including water produced by chemical reactions and various organic molecules. That can be acids, alcohols, or hydrocarbons. This later being often gathered as a family called tars. The solid produced is called char or biochar and is characterized by its higher content in carbon and its higher porosity than the initial material. Now just a small example of biochar that was made from sugarcane bagasse from Colombia. It looks like quite similar to coal, in fact, black shade. An important operating condition in pyrolysis is the heating rate. When it comes to producing biochar, heating rate is usually very slow, similar to the one you have at your oven at home, typically a few degrees per minute, which induces a reaction time of about 1 hour. Such slow heating rate favors the production of biochar that can reach up to 30% of the initial solid. The distribution to remember is that for slow pyrolysis, gas, liquid, and char yields are similar, 1/3 for each. We are not going to talk much here about fast pyrolysis. Fast pyrolysis aims at maximizing liquid. And just for you to have a comparison, the heating rate is in this case of a few hundred degrees per second, reaction time of seconds. And then a liquid yield of about 75%, the rest being equally distributed between gas and char. But let's focus on our product, the char or biochar. Before final use, char is often upgraded to improve its property relatively to the applications. There are two categories of upgrading. First, thermal upgrading, commonly called activation, where the biochar porosity is enhanced thanks to high temperature reactions with reactive gas like steam or carbon dioxide. And then you can also have mechanical upgrading to make the material denser and more homogeneous and hence easier to handle. It can be by pelletizing or briquetting. Here, just to show you a small example of a briquette. These briquettes were made by biochar through agricultural waste in Kenya. But what are the applications of this biochar? Well, how many applications are there? You can guess based on the number of hours. 5? But no, there are much more. A recent article is even entitled The 55 Applications of Biochar. And the first sentence of this article is that these 55 applications are not exhaustive and that more than 200 may actually be mentioned. For a matter of time, I've made a selection of 5 of them among the most mature and relevant for developing countries, as well as some more prospective. The first one is the use of biochar as solid fuel, as more usually called charcoal. The second one is the use of biochar as soil improver to increase crop yields, then as filtration medium for gas or water, additive in anaerobic digestion, or for energy storage in battery. But let's start with solid fuel. Biochar is then used as a substitute to wood or wood charcoal, mainly for cooking in a household or for production of heat and power in the industrial units. Biochar is therefore a solution to deforestation, which is a major issue in Africa, and moreover to air pollution, since biochar briquettes are usually burnt in cleaner stoves, releasing a less toxic gas. One major barrier to this application is non-technical but social. What I mean here is the social acceptance. If you propose people to switch from wood to sludge char for cooking, even if everything is the same, if the efficiency is the same, even if the price is lower, do you believe that people will accept easily how to manage? We will come back to this issue later. But let's move to the use of biochar in agriculture, namely as soil improver. This use can be seen as the most mature and popular application. Biochar is added in fields, and the results show that it can increase crop yields, water retention, and soil stability. It can also be seen as a carbon sequestration solution, since carbon is buried in the soil and released at a very slow rate. This application, while attractive, has some limitations. One of the main ones is that the link between the material used to produce the biochar, the process conditions used, and the resulting biochar quality and performances in the field is not clear. In addition, some performances can be very good on one type of crop, but the effect can be negative on another without any clear explanation and thus possibility to predict it before testing. Other limitations are linked with the biochar amount needed to achieve the performances. As you can see on the illustration, results look good, but require 40% of volume filled in with biochar, which can become problematic at full scale, both in terms of supply and cost. Lastly, the risk of heavy metal release in soil must also be considered when the final material used for biochar production contains such elements in significant amount. But let's consider another application of interest, that is the use of biochar as filtration medium. For this application, I would like to show you two examples. The first one is in water, where biochars show high performance in heavy metal removal. Here you can see a device already implemented in some remote areas, having no access to clean water. This device has been designed by a company that proposes the construction book for free. So feel free to have a look at the book as well as the website. The second application is in gas, where biochar can be used to remove H2S from biogas exiting a digester, for instance. Biochar can be used alone or in combination with compost in a biofilter. A study has, for instance, been carried out recently here at IHE, and the results have shown the increase of efficiency when biochar and compost act together rather than when compost acts alone. Biochar can be used to purify biogas exiting a digester, but also inside the digester. Biochar is then added as a catalyst that would enhance the biogas kinetics and the yield. This use, while promising, is still at research stage, and the mechanisms explaining the effect are not well understood. Is biochar an adsorbent of the inhibitors during the digestion or a surface for the microorganism growth? This still needs to be elucidated before optimization of the process. The last application I would like to present you is a bit more prospective and is related to energy storage. The idea is to add biochar in your cell phone. Where? Well, cell phones use lithium-ion battery. Those batteries and several other devices like sodium-ion batteries, supercapacitors, or fuel cells use carbon. The idea is to replace the carbon used at the moment, which shares a fossil origin, by biochar. This type of application is of very high added value, which makes it attractive. Feasibility of using biochar has already been proven for supercapacitors and batteries. This has been carried out notably in a study on sodium-ion battery in the frame of one PhD student that is carried out at IHE. After an upgrading step, the performances of these biochars from different biomass types appeared to be promising along cycles and competitive with those of commercial carbons. However, as for all applications, the link between the feedstock used, the condition of the production of the biochar, and its resulting performance in the application is still unclear and requires further research studies to make optimization possible. Before going further on with the other process, namely hydrothermal conversion, let me show you just a sixth application already in the market. Walking through my city in Delft, I could buy the whole series of a shampoo, of a shower gel, of a conditioner, and last but not least, I could also buy a toothpaste made up of biochar. I tested them and it seems to work. But okay, Now that we have seen the main step of the biochar value chain by pyrolysis, let's consider the main other possible route to obtain biochar, namely hydrothermal conversion. What is hydrothermal conversion? Well, the best explanation may be simply this. Hydrothermal conversion is very similar to a pressure cooker. In the case of hydrothermal conversion, the feedstock is generally wet, like food waste or sludge. The material may undergo first pretreatment to fulfill the specifications required by the thermal process step. In hydrothermal conversion, drying is not needed, so the pretreatment, if any, is only mechanical and consists in milling if the material is made up of 2 large pieces. When the material is pretreated, it is ready to enter the main step, that is hydrothermal conversion. So what is hydrothermal conversion? It's a reaction of the material that is immersed in water under high temperature and an autogenous pressure. As for pyrolysis, under these conditions, the material releases some gas, such as carbon dioxide, as well as liquids, and gives rise to a solid called char or biochar. Hydrothermal conversion can be carried out at different temperatures. But when it comes to producing biochar, the temperature range is usually between 180 and 250 degrees Celsius, which corresponds to pressures between 10 and 30 bars. The process is then called hydrothermal carbonization. Its heating rate is slow, of a few degrees per minute, and the reaction time is therefore on around 1 hour. The maximum char yield can go up to 50% of the dry solid. What's happening to the solid afterwards? As for pyrolysis, char is often upgraded to improve its properties relatively to the applications. The main difference with pyrolysis is that in the case of hydrothermal carbonization, the char initially contains a lot of water and then needs to undergo first a step of dewatering. Note that this step is much less expensive than drying because the char produced is naturally hydrophobic. After upgrading, the char can be used in the same ways as the char from pyrolysis. So I'm not going to list all of the applications again. Better to use the end of this video to discuss the implementation of this biochar value chain. What is the status of this value chain? In other words, at which stage of development are we? Well, biochar can be seen as an emerging market worldwide. This means that one can see the emergence of demonstration projects and companies both in developed and developing countries. The maturity level varies according to the type of biomass used, sludge being, for instance, more challenging than wood, and according to the production process, pyrolysis being more mature than hydrothermal carbonization, and according to the application. Using biochar as fuel for cooking or as soil improver is more mature than its use in digesters or in batteries. This difference of maturity level also means that there is a need for research and development, and biochar can be seen as a hot R&D topic today. A few illustrations, several conferences focused on the topic this year, networks worldwide, a dedicated journal, and more than 100 of new publications mentioning the term biochar every week. Hot research topic, why? What are the technical issues associated to the biochar value chain? I would say 3 main ones. The first, as in all processes, is the design of technologies that combine as much as possible efficiency, robustness, and low cost. The importance of these criteria can, of course, vary depending on the application targeted and the context. Producing biochar for cooking or for batteries is different. The second key issue is the recovery of the byproducts. Biochar is the main product, but gas and liquids are also released, and they should be either treated but optimally valorized as such, and therefore increase the process viability. The last key issue is the understanding of the link between the feedstock properties, such as its content in inorganic elements, the process conditions, such as temperature, and the resulting biochar properties and performances, for instance, its porosity and adsorption capacity. These issues require to launch systematic studies on a large range of materials, operating conditions, and applications, so as to acquire sufficient knowledge to derive models and then optimize the whole value chain. When developing a value chain, of course, the technical aspects are crucial. However, when it comes to implementation, economy is also a key word, and the business models related. Two questions need to be thought of. First, which actors and the whole value chain from feedstock to product? This implies two sub-questions. Who is willing to invest on biochar production and upgrading? Is it the feedstock producer, possibly gathered in cooperatives, or the biochar end user, or new dedicated actors? And which companies for design, construction, operation, and maintenance of the units? This can lead to indirect benefits for the local or national economy. Second question, which scale and market associated? Microscale with households, for example, biochar for cooking in rural African areas. Small scale with farms, again in African rural areas or other places worldwide. Large scale with industries where waste is gathered, like the huge amount of rice asked in Asia. As shown, the answer is of course not unique and vary with the context. Lastly, one aspect that is sometimes dangerously forgotten in the implementation, it's the public acceptance. Let me just give you an example. A project had been launched in Africa to replace wood charcoal by biogas cook stoves. Technically, the solution was ideal, more efficient, less pollutant, and not expensive. However, users never used these cook stoves because the food taste was not the same as the food cooked with wood charcoal, the taste that all of you know. So, this example shows the importance of adopting from the beginning of projects a multi-actor approach and training activities to raise stakeholders' awareness, for instance, on the issue of air pollution with cooking, of pathogens in waste, and of the opportunities of the new value chain created thanks to biochar. But lastly, I would like to highlight one aspect that cannot be neglected. We can make all the awareness campaigns, but we cannot forget marketing. One example to end with, you remember the toothpaste I showed you. If you are the salesman supposed to sell this amazing black toothpaste to whiten the teeth, you can feel a bit unlucky. But all becomes easier when Hollywood actresses start to advertise the product for you. And then you start finding biochar black toothpaste in the trendy shops of Delft. Well, I would like to thank you very much for your attention. I hope you enjoyed the video and feel more informed about the biochar value chain. Feel free, of course, to contact me if you have any questions.